Hi guys, Miss O'Connell here. So we're going to review the Impulse Lab that you completed. Okay, so in the lab, your job was to basically look at how impulse momentum vary when the force being applied, the time period of application, okay, and the mass of the object vary. Okay. So our first question is, why should you shut off the extinguisher before he reaches the red line? So that red line represents a photo gate, okay? And in the purpose, it explains what a photo gate is used for. It's used to determine the amount of time that it takes an object to move a specific distance. So in order to measure the final velocity of Wally, the extinguisher must stop applying a force, okay? When the extinguisher is applying a force, Wally will accelerate, which means that the velocity would change every second. Okay, if the velocity changes every second, it's impossible for us to figure out his final velocity. Okay, so the force must stop being applied for us to find a final velocity. So we must shut off the extinguisher before that point. Okay, so if you do hit shut off, meaning that there is no force being applied, we can assume that Wally's moving at a constant velocity. Okay, if there are no external forces acting on him after the extinguisher shuts off, then we know that he's moving at a constant velocity because of Newton's first law. Okay, so both the first and the second law apply here. The second law can be used to explain the portion of Wally's motion when the extinguisher is firing. Okay, so that net external force causes Wally to accelerate, meaning that his velocity will change, aka his momentum will also change. The first law explains that after we turn the extinguisher off, that Wally will continue to move in a straight line at a constant velocity until another external force acts on him to stop or change his motion. Okay, so both the second and the first law here are explaining or expressing his motion. Okay, and then of course we know that the impulse momentum theorem, okay, in which we've talked about, right, impulse is equal to the change in momentum. This equation comes from Newton's second law. Okay, so force times time equals mass times the change in velocity. If we were to divide both sides by the time in which the extinguisher is applied, we basically get here that the force is equal to m times the change in velocity over the change in time. Okay, we know that change in velocity over change in time is equivalent to the acceleration. So basically, this equation that we've been using is derived from Newton's second law, F equals ma. So a force over a time period will cause a change in momentum. Okay. Question 4 asks, what is Wally's speed before the extinguisher is applied? So before there's a force applied, the velocity is 0, right? If there's no force applied and the object's at rest, it remains at rest. Okay, number 5. Okay, number 5, how do you determine the change in speed? So if you took a look at that video that I recorded before you did the lab, you would have realized that you can use the constant velocity equation or the average velocity equation to determine Wally's velocity or final velocity. So due to the lack of external forces after the extinguisher is shut off, we know that he'll move at a constant velocity. Therefore, you divide the distance between the photo gates, 10 meters, by the time it takes Wally to move through the gates. Okay, and you'll find the final velocity. To convert from millisecond to second, you divide by 1,000, aka you move the decimal point over 3 times to get seconds. Okay, in our previous video, we discussed how to collect some data. So let's talk about the post data collection questions. Okay, so how does increasing force time, meaning how does increasing the amount of time that the force is applied impact Wally's speed and momentum? In order to truly measure that, right, we need to make sure that the force applied by the extinguisher and Wally's mass are constants. Okay, they're controlled variables. We can either increase or decrease the amount of time that that constant force is applied. Okay, so let me show you what I mean here. So if we activate that force and we let it run a few meters before we hit the photo gate, okay, our force time is 5,754 milliseconds. Okay, our force and our mass are constant. Okay, so I'm going to do the calculations really quick, and I'll show you the result. Okay, so we see that the force time would be 5.745 seconds. Okay, the speed, the final speed, or change in speed, ends up being 15.9, and the momentum is 1,112.88. Okay, so we're going to do a second trial in which we need to keep force and mass constant. We can either increase or decrease the amount of time that that force is applied. Okay, let's see what happens. So I'm going to click reset. This time I'm actually going to increase the amount of time that the extinguisher is applied for. So I'm going to activate and allow it to run for a longer period of time before I shut it off. So that time I waited right before it hit the motion detector rather than a few meters before the photo gate. And this time, my force time is 7.02 seconds. So let's see how speed and momentum change. Okay, so we see that when the amount of time that the force is applied for increases, our speed also increases, goes from 15 to 17 meters per second, and therefore our total momentum also increases. Okay, so if there's an increase in the amount of time that the force is applied, there will be an increase in this final speed or change in speed, and the momentum or change in momentum of the object, so long as the force and the mass of the object remain the same. You might be thinking to yourself, right, we just talked about that impulse equals change in momentum, right? So this column here should be equal to this column, right? Theoretically, the change in momentum should be equal to the impulse. And while they're close, they're really close, okay? That error has to do with the fact that we're using a simulation, okay? That we don't stop or shut off the extinguisher right before it hits the photo gate perfectly each time. Okay, that's going to affect the data. So theoretically, impulse and change in momentum are equivalent to each other. But in this simulation, we might see some slight differences because, again, it's a simulation. Okay, so let's head to number 9. Okay, so that next question, number 9, how does increasing the extinguisher's force impact Wally's speed and momentum? So if you see the first 2 trials up here, if we take a look at force, right, as we increase the force from 115 to 175 newtons, as long as our mass stays constant, Wally's speed increases from 15 to 19, and the momentum increases from 840 to 1097. Okay, so you see an obvious increase there. If the force applied increases, the change in the velocity as well as the momentum of the object changes, right? And that makes sense because this theorem is related to Newton's second law, F equals ma. So larger the force, larger the acceleration, which means larger the change in the velocity, and momentum is directly related to velocity. Okay, so let's take a look at number 10. So if you look at these next two rows here, if we increase the mass, so if we go from 55 kilograms to 70 kilograms, and force stays constant, we see that the speed actually decreases, okay, and the momentum actually decreases. All right, so if you have a constant force and our mass increases, the object's velocity will change less, okay, because the more mass that you have, the more inertia you have, the more resistant that object is to a change in motion. Okay, so Newton's first law, the law of inertia, explains this here. Okay, so how does increasing Wally's mass impact speed and momentum? As mass increases, Wally's speed and momentum will decrease as long as the applied force is constant. This is because of Newton's first law. The more inertia or mass an object has, the more resistant it is to a change in its motion, aka its velocity. Okay, so number 11, how do the products compare? So write an equation to show the relationship between force, time, mass, and change in velocity. Okay, so that is our change in momentum is equal to the impulse. So the impulse momentum equation. So you have force, applied force, over application time or contact time must be equal to the mass of the object times its change in velocity. Okay, so that's the equation. Ooh, that is not a good box. That's the equation for number 11. Okay, number 12, definition of impulse. So in order for an object's momentum to change, a force must be applied. Impulse is the product of the applied force and the time of contact. Okay, impulse is basically a measure of the ability of a force to change an object's momentum. Okay, that comes directly from your notes. Okay, we know that impulse relies on force, which is a vector. Okay, vector meaning it relies on direction, so therefore impulse is also a vector. What does it mean if impulse is negative, or the force is negative? Okay, so if the force or the impulse is negative, that means that that force causes the object's momentum to decrease. So the object will go from some velocity to 0. If impulse is positive, meaning that the force is positive, that force causes the momentum of the object to increase, like in this simulation. So it goes from some initial velocity of 0 to some positive velocity, greater than 0. So feel free to unsubmit your lab from Classroom and make whatever changes you need. Maybe even print it out, put it in your notebook.